So any object that has mass, and it could be perhaps an astronaut here, any object that does have mass, around them has this gravitational field, and it is always this attractive force. And basically it interacts with other objects that also have mass, and if you had just these two objects out in space, eventually the two of them would start to move together. Now, what I'd like to look at now are the forces between these objects. And effectively what we have is the interaction of the field around this with the field around this. Now, if we have two objects, maybe both of the same mass, they're going to feel an attractive force towards each other. What we could do though, is perhaps we could increase the size of that attractive force by making one of the masses even heavier. And if we do that, there's going to be a bigger force of attraction between the two. And we can say then that the force is proportional to the size of this mass, which I'm going to call m. But also, if we were to make this mass bigger, perhaps we replace it with something a lot larger. Again, there's going to be a bigger force of attraction. And remember, Newton's third law means that the attractive force of this on this object is the same size as the force of this on this object. And basically, we can say then that the force is proportional to the size of this mass as well, which I'm going to call little m to show it's a different mass. Now, the other thing is that if we maybe take these further apart or bring them closer together, the size of that force is going to change. And as we bring them closer and closer together, which we can maybe measure the distance between the centre of these two masses, so we can look at the distance from this point to this point, we can also look at how the force is proportional to 1 over r squared. Okay, and the reason is it's an r squared because we're not just talking about one dimension, there's like sort of 3 dimensions in these sort of fields in all directions. And basically this 1 over r squared relationship is really important. That means you double the distance away from something and the force goes down by a factor of 4. Okay, and again we're talking about the distance from the centre of this mass to the centre of this mass. And effectively what we can do is we can bring all of these 3 equations together to say that the force is proportional to mm over r squared. And what we've got now is the beginnings of some kind of equation. What we need now is some constant of proportionality, and we can say then that F is equal to g mm over r squared. So here g, this constant is what we call the gravitational constant, not particularly original, and the value of g can only be found by experiment. So if we maybe have a couple of masses, we know how far apart they are, we can measure the force between them. We can say that g is equal to 6.67 times 10 to the 11, minus 11, sorry. So this is a very, very small constant, which means actually the size of the gravitational force is really, really small. It's actually smaller than all the other forces that we have, but because it acts over such a long range and the masses of things are so big, it's this gravitational force that really sort of moulds the whole universe. And the units for this are newtons meters squared kilogram to the -2. So this is, I don't think you need to remember the units necessarily because it's often in your data book, but you need to be aware of the size of this. Now the other thing is that gravity is only ever attractive, and these forces only ever pull things together. And to show that the force is attractive, I'm just going to put in a minus sign down here. So that all this minus sign means is that the forces are attractive. Whereas if you have maybe an electric force, it can either be attractive or repulsive. And this thing here is what we call Newton's law of gravitation. So really, Newton doesn't just have his first, second and third law, he's got this law as well. And he was one of the first people to kind of realise about this interaction between these objects. And basically it states that the force between two objects is proportional to the product of their masses and inversely proportional to their separation squared.